Okay, very good. All right, well, I'm absolutely delighted to be able to join you guys, and I very much thank the conference organizers for the invitation and for finding a very creative way of dealing with the perennial problem I pose at these meetings. So thank you very much. I'd like to talk about some work that's really a report, a status report of something that's occupied a lot of my thinking and efforts over the course of the pandemic, something which is right at the moment, I think, in a very exciting place. We don't understand everything about it yet, but I want to tell you what we do understand about it, and hopefully set things up for what should hopefully be the final installment of the talk on this subject at whatever the next relevant Amplitudes meeting is. This is work that really has its genesis in the work of Song and Yuntao Bai and Gongwen Wang on the ABHY realization of the Surfacehedron and tree-level scattering amplitudes in trace phi cube theories. Has another big leg and motivation from the general picture of stringy canonical forms and binary geometries that was also developed with Song He and Thomas Lam. But this work and the sort of status report, as I said, over the course of the pandemic is been in collaboration, wonderful collaboration with Hadley Frost, Pierre-Louis Tamondon, Julia Salvatore, and Hugh Thomas. Okay, so I've begun with some version of this slide in every Amplitudes meeting for the past decade, so I won't go through it in detail. But the overarching question that a number of us have been pursuing for all this time is to find a different question that really lives in the kinematic space that defines scattering processes, to which the amplitude is the answer, rather than thinking about amplitudes as the unitary evolution in Hilbert space and local causal evolution in space-time. So we'd like to see the rules of quantum mechanics and space-time as outputs and not inputs. And what we've been seeing over the past decade, but really starting in 2017 directly in kinematic space, is a set of ideas that involves some combinatorial geometric objects that live directly in kinematic space. So positive geometries in kinematic space that began with this sort of kinematic space description of what the amplituhedron is in the work with Hugh Thomas and Yara Trinka back in 2017, and then that opened up the sort of possibility of thinking about very general theories in this way, and led to this ABHY picture of the isosahedron for trace phi cube theory. Various avatars of it have been generalized in beautiful papers by others to phi to the p theory for general p. And this was developed through to the end of 2019 through to one loop as being associated with cluster algebras and cluster polytopes. So that's the sort of jumping off point, and that's what sort of teed us up to be able to work on this subject very intensively over the course of the pandemic. The broad clues that there is such a structure in kinematic space that we should be looking for is, first of all, the very striking fact that really goes back to Stashev's original realization about the amazing properties of the isosahedron, that if we just imagine all the cubic graphs for a phi cube theory, the planar cubic graphs in a phi cube theory, that all of those diagrams could be arranged as the vertices of an interesting polytope where all the facets reflect partial factorizations of the amplitude. That's a highly non-trivial property, highly non-obvious property, that the pole structure and what poles go together, the compatibility between poles, has a polytopal character. Now that remarkable observation is associated with a hidden symmetry that the amplitudes have. And the symmetry becomes manifest when you talk not about the scattering amplitude directly, but about a differential form that lives in kinematic space. So if we think about the kinematic variables, it's just loosely here denoted by the x's. These are the momenta squared and all the propagators. Then we might think that every Feynman diagram is just the product of 1 over the propagators, but we uplift that to a differential form that lives on the space of the Mandelstam invariants. So instead of 1 over x, we look at the sum of dx over x, or d log x. But they have to be weighted with particular signs. That's the non-trivial thing. It's possible to weight this form with non-trivial signs such that the form is actually only a function of the ratio of the x's and not of the overall scale of the x's themselves. So we call this projective invariance. And in general, there are many, many, many more equations than signs to be chosen in order to check whether the form is projectively invariant. So it's highly non-trivial that it's possible to assign signs to each one of these forms to make the entire form projectively invariant. Nonetheless, this is something which is a direct consequence of the existing of the underlying polytope structure. And this projective invariance is an analog for trace phi cube theory of dual conformal invariance for n equals 4 super Yang mills. And as dual conformal invariance does, this too has consequences for the amplitude. It implies that the amplitude vanishes more quickly than you'd expect in certain directions in kinematic space, and is associated with new recursion relations to write the amplitude in a way that makes the symmetry manifest term by term. All right, so now this is the form, and we can take the form and pull back to a certain subspace. That's a subspace defined by ABHY to get the actual amplitude. So if you take this form and you pull it back to an appropriate subspace, and you pull off the overall volume form, you get the actual amplitude. So this is also not obvious, that it's possible to take this form and pull back so that all these minus signs go away and just get all sum with all plus signs. Okay, so all these 3 things are sort of qualitative clues to the existence of this underlying structure. Okay, so what we're going to do now is talk about, let me just tell you about the theory that we're going to be talking about, or at least start off talking about. We're going to be talking about trace phi cube theory to all orders, so to all loop orders and all orders on the 1 over n expansion. So it has nothing to do, it's a non-supersymmetric theory, it has nothing to do with planarity, it has nothing to do, and has nothing to do with, it's a non-planar, non-supersymmetric theory. We are working though in the 1 over n expansion. So in the 1 over n expansion, we use double line notation to draw, if we're drawing Feynman diagrams, so these are some representatives for 5-point scattering. This is tree level, this is some 2-loop planar correction. This is a 1-loop double trace correction. This is a 1-loop single trace, but higher orders than 1 over n correction to a single trace amplitude. And all of these things can be dually drawn. The duals of these graphs are certain surfaces. Okay, so and they're in fact triangulations of surfaces. I'll review this again in a second. But just the 0th order point is that we just have the sort of standard connection between Feynman diagrams and surfaces of various genus. So we go from a disk to having 2 punctures, to having an annulus for this double trace guy, to having this torus with a single puncture and a boundary component with the 5 guys, since we're talking about 5-point scale. All right, so the things that I want to talk about is first, just in the field theory limit, and just talking about the integrand, the usual stomping grounds so far of the story of positive geometries. We'll be going beyond that in this talk. But so first, I want to tell you about what the all-order amplituhedron is for this trace phi cube theory. Now, the beginnings of this were already there in my talk at Amplitudes last year, where we called these objects clusterhedra, and they were really sort of moving directly off from the 1-loop story that we had seen associating these objects with cluster polytopes. As we'll see that while the cluster structure is almost exactly what's needed, it's not quite exactly right. Okay, so we're not calling them a clusterhedra anymore because they're not really associated with the cluster algebra, and instead they're really more directly naturally associated with the surface. So that's why we're calling them surfacehedra. Okay, so this is something that I think we've understood since the winter and has been talked about in a number of talks. And what we've been doing since then is moving on, trying to see how much of the story that we understood before can be extended to again the entire structure. So all loop order, all orders in 1 over n. And here the key idea was that of a binary geometry associated with these polytopes. I'll review what this is, but But in the old story at the tree level and at what we'd understood at one loop, and even the one loop story is part of what's being slightly modified as we go from clusterhedra to surfacehedra. So I'll be giving you a simpler picture of what's going on at one loop and a more complete picture of what's going on at one loop. But in any case, for all of these surfaces, we now understand that this notion of a binary geometry generalizes, and that allows us to define the notion of stringy canonical forms and the corresponding string amplitudes for all surfaces. And what we're doing now is smack in the middle of exploring what these amplitudes look like, what their analytic structure is, what kind of functions you get, and what's really going on with these amplitudes that now make sense. They have a new parameter alpha prime, just like string amplitudes, and what they look like. But what I'll tell you about are some preliminary observations about them. They have the same qualitative structures, all the same qualitative structures as real string amplitudes, as we'll see. And so we don't know what these things are yet. We don't know if it's a new kind of string theory, a new view of what string amplitudes are. I suspect it's likely going to end up to be a new view of what string amplitudes are, perhaps from a more flexible point of view. But anyway, we don't know what they are, but I'll tell you what we know about them and what we're trying to understand. And much of our work in moving beyond the kind of standard so-called finite type cluster cases, where there was some sort of theory to explain where these binary structures came from, the second we move off to what's going on for general surfaces, we had lost all we had lost the sort of moorings for exactly systematically what to do, so we were just more artisanally hunting around for how to think about the binary structure and where these variables come from and how to construct them. And in small enough examples, it's possible to do that, and that's mostly what I'll do in this talk, in the body of this talk. But what we've also understood is the systematics of where this comes from, or at least the beginning of the understanding of the systematics of where this comes from. And this has to do with not the cluster structure directly, but a new structure in Quiver categories that underlie this binary map. Something many of you know the great Steve Shenker. And I learned from Steve Shenker a long time ago something that I call Shenker's theorem, which is that subject you hate/fear the most will next be the most relevant to your research. And I never in a million years thought 10 years ago that I would be learning category theory in order to think about physics, but here we are. And this is really a place where it has real beef and teeth, and is a deep, more abstract, but sort of deep origin for where a lot of this magic is coming from. I suspect that in the body of this talk, the part for which I have slides, we're going to have a lot to do already. So I'll probably get to talk about the first two things. And then when we end and we clap, for those few of you who might be interested to hear more about about Quiver categories and where the binary magic comes from, I'll be happy to do that just after we clap. In real time, not with slides, but just explaining things in real time. All right. So let's get started. So what are surfacehedra? Again, the claim is that given any surface, and remember the surface are just the surfaces that characterize the particular order in the one-of-N expansion and the trace expansion for the trace phi cube theory. For any surface, there's a polytope. There's a facet associated with every arc, a homotopy equivalent class of arcs on the surface. And while in small examples, there's finitely many of these, generically it's infinite. So that means that, and we'll understand where this infinity comes from and what it means. But that means that it's a infinite polytope that has a sort of a fractal structure. So you can draw it in a finite region. But if you zoom in on the facets are sort of shrinking and getting smaller and smaller, and there's infinitely many of them. So that's an interesting fractal structure. Now, the vertices of this polytope, as in the story of the isosahedron, are Feynman diagrams. But the facets, remember, the facets are associated with arcs, and arcs on the surface will be associated with propagators, as I'll review in a second. but the facets reflect a geometric feature of cutting or pinching the surface. So, for example, if I have the disk and I have an arc X, I can see what happens when I pinch X, and when I pinch it, the surface factorizes in two. That's a familiar way that we understand from the worldsheet where factorization comes from, but it's just a basic fact about the factorization of the surface. Similarly, if I have a surface with a puncture here, and if I have this arc X, if I cut along X, I open up the surface as much like a forward limit when it comes to an amplitude. There's another class of arcs in the surface that are very interesting. They're closed loops, and as we'll see, these guys that go from boundary to boundary correspond to propagators of the trace phi cube theory. These guys that are closed loops in the surface do not. But they're also there. They're forced on us by the geometry of these polytopes. And they also are associated with the canonical factorization, which is what you get from pinching the surface along the closed curve. So if I have an annulus, which is the first time this happens, and I pinch along delta, I get the product of two disks each with a puncture here. Okay, or if I have a four punctured sphere and I take one of these closed red circles and I pinch it, I get the product of two spheres, again, with an extra puncture where I did the pinching. So the claim is that the polytope has has a facet for each one of these arcs. And furthermore, when you go to that facet, what it looks like exactly reflects the cutting and pinching of the surface. This new stuff is associated with new poles in the canonical form that we associate to these polytopes. And so there's a new kind of particle that's there in the integrand for the amplitude that was not there in the trace phi cube to begin with. And as we'll see, it has the interpretation of some kind of quote unquote gravity. Okay. And of course, this picture is this is the earliest hint of some similarity between what's going on in this story and with standard string theory, because of course this picture, and literally with the annulus, is also the first place in which, even if you're only talking about open string amplitudes, you discover the necessity of having closed strings.
Nima,
Okay, just so
can
you
I
see
ask you
that there are very
something?
concrete pictures associated with this. I'm just drawing for a bunch of surfaces. So this would be a tree level, one loop, a planar, a two loop vacuum diagram, one loop double trace, and a two loop vacuum diagram. So these are representative Feynman diagrams associated with each surface. These are the polytopes that are associated with them. And as you'll see, beginning in these cases with an annulus or the torus, you see the sort of infinity that I was mentioning before, and an even more crazy infinity associated with this picture. That's the picture of the torus with the sort of fractal structure here. On the right-hand side, I'm showing a projection of this three-dimensional picture. When you look from the top, where you see this fantastic-looking object. Whereas you zoom in, you see more and more and more facets in this sort of fractal structure. Okay. Okay, so let me just say a few basic things in order to lay the groundwork for what we'll be discussing. So again, we're talking about trace phi cube theory. So here's the Lagrangian we're going to be talking about. I'm only going to be writing down the trace phi cubed interaction. Now, by symmetries, I could also write down trace phi squared trace phi, or just trace phi all cubed. But I'm only writing down the G trace phi cube interaction. And when I do that, then I have a standard double line notation for all of the amplitudes, the usual topological expansion. Okay. All right. So now there's a very standard but very nice fact that that the triangulations of orientable surfaces are exactly given by these double line notation fat graphs or ribbon graphs. So let's say you didn't care about these ribbon graphs, but you cared about the surfaces. So let's say you have this surface or any of these surfaces, and you want to give a triangulation of the surface. Well, if for simple enough surfaces, it's clear what we mean by a triangulation. But more abstractly, what we mean by triangulation goes the other way. More abstractly, a triangulation defines a surface. And what is a triangulation? It's a collection of triangles, and the triangles are x, y, z. You think of the x, y, z as being the edges of the triangulation, not necessarily the vertices. Okay, so it's a collection of edges of the triangulation x, y, z. I'm allowed to have let's say both a little x and a capital X, and I think of capital X as being oppositely oriented to the little x. Okay, and so the rule is that if a given x is repeated, either as itself or its capital, we have to have both of them. Okay? Or it can only occur singly, in which case it'll be a component of the boundary of the surface. So that's abstractly, without drawing a picture, what a surface is. It's a triangulation, and a triangulation is just a collection of x, y, z's, where each x can come in a lower or uppercase variety. And if it's repeated twice, it can at most be repeated twice, and in that case, it has to come in one lowercase and one uppercase. Right? So that determines a surface. And now the vertices are determined by those rules, because you now demand that you write any little x as some vertex prime, and the capital X as the oppositely oriented vertex prime vertex, in such a way that all those assignments of the vertices are compatible between the different triangulations. So that means, for example, if I have a given x, y, z, that now the vertices are thought of as the lines in this double line notation diagram. So in this way, a single trace phi cube diagram, just one, defines a triangulation of a surface. So you just want to think, not all of them together, but just one diagram defines the triangulation of a surface. Okay, so here I'm just drawing the same things again, the same triangulations and the corresponding trace phi cube diagrams that define the triangulation. Okay, and now what are now the rules for translating between a picture of the surface and a graph? The edges of a graph are chords of the triangulation. The double line colors of the graph are vertices of the triangulation, and internal closed color loops are punctures in the surface. So, okay, so that's the most basic thing. At the most basic level, the graphical relationship between the triangulation and trace phi cube double line notation diagrams. Okay, now there's something else that we can naturally define, which is if I now draw an arc on the surface, we just saw in our simplest examples that they correspond to sort of propagators of the corresponding Feynman diagram. But we can in fact naturally assign momenta to them in the following trivial way. Let's go back to the surface. We know in the case of the disk that we're supposed to assign to this arc that goes between, let's say, pi and pj, the sum of all the momenta in between. Okay, but we can actually say that slightly more invariantly by saying that we assign x the same momentum as this collection of arcs, 1 to 2, 2 to 3, all the way up to j minus 1 to j, because the arc x is homologous to that arc on the boundary. And that's the general idea, that the momenta are associated with the homology of arcs. So, so let's say I now talk about this one loop example. Okay, so there's one puncture on the inside. So this is one loop. Now I need to give a basis for the homology. So so I can give the momenta on the outside, and I have to specify one more. So let's say this one I call L, but then the momenta that I assign for everyone else is completely determined by the homology. So the momenta for this arc X is given by L plus P2 plus P3, because X is homologous to L plus P2 plus P3. Similarly, in this example, if I have this arc and I call that L, then the arc for this arc, then the momentum for arc X is L plus Q, where Q is the total momentum on the inside, and for the blue arc is L minus Q. In this way, we unambiguously assign loop momenta to every chord, so every triangulation, And therefore, every triangulation of the surface, remember, a triangulation of the surface is a Feynman diagram. And that means to every Feynman diagram, we unambiguously associate loop momenta to that diagram. So this allows us to label, to give unique labels to the loop momenta of any diagram. But of course, there is a cost, which is that there's infinitely many different triangulations that correspond to the same diagram. Okay, so that means that if we think of an integrand, the integrand, that there's no canonical way of sort of choosing one copy of all the Feynman diagrams. You can do that. It's like choosing a fundamental domain, and in fact, it's literally the issue is literally that the surfaces have a non-trivial action of the mapping class group, and so we have to choose a fundamental domain. So there's an issue of choosing a fundamental domain at the level of the integrand. But if we don't want to do that, if we just literally take the integrand, in these cases beginning with the annulus, we'll just get infinitely many copies of all the diagrams. And so if we did the loop integral, we'd have some extra factor of infinity multiplying the whole thing that we have to take care of. So either take care of it by choosing a fundamental domain at the level of the integrand, or doing something else, and we'll come back to talking about that a little bit later. But again, here's an example already in this very, very simple case where we have these are just diagrams for the same bubble. Okay, but when I go between two different diagrams and I define this thing to be L, then I get different assignments of the momenta for the same diagram, and I can just keep doing this. I can keep winding this picture around more and more and more and more. At the level of the actual Feynman diagram, it's exactly the same. The arcs are different because they wind around more and more and more, and they're related to each other simply by shifting L goes to L plus P to L plus 2P, and so on. Okay, so that's the action of the mapping.
Can I ask you here? So do you know in advance which cuts does your integrand match? If you may,
it matches all of them. Okay, it matches all of them. So
well, normally you have to relabel, right?
No,
so,
there's no relabeling here.
I
can maybe you can ask. You see, this is different than what happens if you're talking about trying to do it for a permutation invariant theory like gravity. Here, once you have the surface, we know which genus we're talking about, and then it's totally unambiguous. Okay?
So you are matching the single cut L square is 0. Is it
no, we match every cut as it's supposed to be matched. That's the entire point of these polytopes, is that a cut corresponds to taking a given propagator and cutting it, and that opens up the surface. Now, exactly the thing is what the same propagator shows up infinitely many times. So whichever representative you choose to cut, you can cut that one in the integrand and you'll get exactly the correct residue on that cut.
But if you are matching all cuts, well, what is the point of considering all these windings, right? I thought you are and adding more windings, match more cuts, more cuts, more cuts.
Right, because there's no canonical way of choosing one copy of everyone. You can do that. There are many ways of choosing one copy of everyone. Or two copies, or n copies of everyone, if you like. There are many ways of doing it, like there's many ways of choosing a fundamental domain. But there's not a canonical way of doing it. If you choose one way, then you will match, then you have a concrete set of labelings in that way. And then when you cut, it descends to a particular set of labelings for the lower product. But the choice of how the fundamental domain was chosen at the top will dictate what the corresponding choices of fundamental domains look like after you factorize. Okay, so I don't want to talk about the choice of fundamental domain at the level of the integrand, because when we're going to be talking about the amplitudes, there's going to be a different way of dealing with this issue, which looks a little bit more natural. But it certainly is possible to talk about the fundamental domain at the level of the integrand as well. I'm not going to talk about it here, but that has been talked about in some of the previous talks on this subject. Okay, so finally, I want to make another important point that while the momenta are labeled by homology, we actually care about the actual arcs in the problem up to homotopy. So here's an example. So here I have arc X and arc Y. Arc X and Y are homologically exactly the same. There's no momentum associated with that puncture. So the momenta that I would associate with X and with Y, but by rules of homology, are exactly the same. However, it's very important that we distinguish X and Y in our approach. That's because X and Y here, for example, this triangulation looks like that. These are the lines on the other side of a bubble. And if we wanted to associate a form with this, we'd have if we want to associate a form, we'd have 1 over X times 1 over Y, that if we identify X and Y would give us a double pole. Or if we wrote it as dx over X, dy over Y, and again, if we associated X and Y, we wedge them together, we get 0. So either we get a double pole or we get 0, both of them are not good. So it's really important that we distinguish X and Y. And in general, for example, at one loop, we'll have an xij and an xji, and they're different variables. Okay, so we're just warming up to define our object. So let's now talk about what the space of kinematic variables is that's associated with the amplitude. Okay, so the space of kinematic variables is all the homotopy classes of chords on the surface. And as I've said, it's generally infinite, beginning in this case of the annulus, because these propagators, there's no I can define L or L plus any multiple of the momenta on the inside or on the outside. Okay, so we have all of these arcs, and we also have another set of arcs that don't show up any one of the trace phi cube diagrams. As I said, these are sort of closed loops on the surface that we generically label with delta, and the momenta the p squared that we associate with that is the sum of all the momenta on the inside or on the outside squared. Okay, so these guys are an integral part of this story. So the kinematic variables are the set of x's and the deltas, which correspond to open and closed loops on the surface. All right, another final little point that we'll see in a little more detail in a moment is what happens when we have punctures. There's something slightly unusual going on. So let's say we have this picture already just at one loop. Now, you might think that you want to draw like a chord, that this would correspond to one of the loop propagators that I drew in my examples. But from the perspective of the surface, there's actually 2 kinds of loop variables. And this is made perhaps a little bit more clear if you imagine that if instead of having a puncture there, you had just a single trace term with so a little annulus with 1 marked point on it. And imagine what would happen as that momentum goes to 0. So clearly, if the momentum of that particle goes to 0, you shouldn't really be able to tell that it's there. And that annulus, the internal annulus, should sort of be replaced by a puncture. But if this was opened up, then I can talk about loops that wind around this guy clockwise or counterclockwise. And those descend as the momentum goes to 0, not to an infinite number of things, but to 2 different kinds of chords that keep a memory of whether the chord upstairs was circling clockwise or counterclockwise. Okay, so in the cluster literature, this is referred to as tagging. We can think of sort of positive or negative winding variables associated with the puncture. Well, that's something that we'll come back to. Okay. All right, now I'm almost ready to define what surfacehedra are. So as usual, we first find the kinematic space. So this is the kinematic space that we live in. We've now labeled the kinematic space as being associated with the arcs on the surface. And remember, to even define the surface, I have to give you some triangulation to begin with. So you give me some fixed reference triangulation. I can think of that fixed reference triangulation as a fixed reference trace phi cube diagram. Okay. Now, having done that, there's a natural set of relations that you can write down between these kinematic variables. All of this actually is forced on you when you think about the very simple ways of labeling these curves by intersection numbers, and this is related to tropical geometry and all kinds of wonderful things. But you don't need to know any of that in order to just see what the simple formula is. So let's say you have two curves, x and y, and the curves cross. Well, if they cross, there's a unique way of uncrossing them. Now, in general, if you just draw the surface abstractly, there's a unique way of uncrossing them. Like if the two curves are like that, I can uncross them upstairs, or I can uncross them sideways, upstairs and downstairs or sideways. However, once you associate them with a particular triangulation of the surface, then there's a unique way of uncrossing. So, for instance, if I'm going to denote my surface now by the fat graphs. It's actually a very convenient way of denoting the surface. So this is the surface that corresponds to a disk with 4 marked points on the outside. And let's say I take this chord x and this chord y. You see they cross, but there's clearly a unique way of uncrossing them that doesn't involve doubling back on the along the corridors of the diagram. Okay, so if I want to uncross them, there's a unique way of doing it as A and B. I could have done it the other way. I could have done it sideways, but that would involve doubling back on along some of the corridors. So there's a unique way of uncrossing them without any doubling back. And these are uncrossing or skein relations that are now uniquely fixed. So if you give me two crossing chords, then x plus y has the unique right-hand side. Okay, and I can also have, for instance, things that involve a chord and one of these deltas. Okay, so if I take this plus a delta, then if I draw it on the corresponding Feynman diagram, I discover that the unique thing that I get is this guy winding around once more. So in this case, if I take a positively winding guy and I add it to delta, I get an even more positively winding guy. Whereas if I take a negatively winding guy and add delta, I get an even more negatively. So those are relations. Okay. Having said that, this is the sort of conceptual definition of the surfacehedron. Very much as we've seen in many places in this story, in the positive geometry story, you go to kinematic space, you find a natural positive structure to impose in kinematic space, and then everything follows from that. In this case, the kinematic space is just given by all of these x's that are associated with arcs on the surface, and we just demand that they're all greater than or equal to 0. This is very much like the ABHY story for the isosahedron. But we further have to impose the conditions that all the relations, the skein relations between any pair of crossing variables has a positive right-hand side. They're fixed to constants, and those constants have to be greater than or equal to 0. All right, so that's the abstract definition of what the surfacehedron is, but it's highly non-trivial that it's possible to choose these CXYs for this polytope not to be empty, and in particular, in the cases where we have infinitely many variables, for the infinite polytope to exist. Okay, so there's a big story that we don't even have a complete proof for yet, but it works in all the examples that we've looked at, that it's possible to do that, but the CXYs have to be chosen in a very particular way in the infinite limit in order for the infinite polytope to exist. If I make a connection with what I talked about at Amplitudes last year, that was before we knew how to take the infinite limit. So then we were talking about truncating these pictures to a finite number of variables, and then being confident that this polytope existed. That's a little bit like learning to do quantum field theory by first doing it on the lattice. And then after you're confident that it makes sense on the lattice, then there's a delicate way of taking the bare couplings to 0, or scaling the bare couplings with the lattice spacing to make sure that the continuum object exists. And there's an analog of that here. These CXYs have to be scaled in a very special way, especially in the case where we have infinitely many variables in order for this object to exist. But it appears to be possible. It's possible in all the examples that we've looked at. We conjecture that it's always possible. Okay, now just to give you some pictures for what these look like in a little bit more detail. So here are some examples at one loop. of what the for example, the bubble looks like a hexagon, and here are the vertices of the hexagon are all the triangulations of the disk. These all correspond to they correspond to the bubble graphs or bubble graphs for the tadpole. I'll show what this looks like more systematically in a bit. This is what it looks like for 3.1 loop scattering. We can look at the three punctured sphere. Now the three punctured sphere is just a trace phi cubed amplitude goes. It's just a two loop vacuum diagram. But even this two loop vacuum diagram has a rich structure because as far as chords on the surface go, there's a lot going on. Okay, so as far as chords on the surface go, we have many different kinds of chord. And again, I'm not showing how this works in detail, but these highlighted facets are reflecting the various factorizations of the picture to a lower object. For example, here, if I look at this green guy, then if I pinch along this green guy, what I'm supposed to see is just the 2.1 loop problem, and indeed that's the hexagon that I see over here. On the other hand, if I pinch along the red guy, I'm supposed to see effectively a forward limit, which is the 5-point tree problem, and that's the pentagon which I see up here. And you can decorate all the vertices of the picture on the right with the defining diagrams for the trace phi cube theory at 1 loop here for 3 points. Okay, so similarly here, all of the facets of this guy reflect the different factorizations that you get from the cutting and pinching of the surface. This is a particular, I'm just showing you all of the three-dimensional polytopes that we've seen, just because we can draw them. Now here's the first really new and interesting example, which is the annulus with 2 points on the outside and 1 point on the inside. So this is a double trace 1 loop amplitude. And here we see that this interesting infinite object. You see these infinitely many facets getting skinnier and skinnier and skinnier and skinnier. All of these guys, all of these facets have interpretations in terms of cutting the surface in obvious ways. For example, if I cut along this red guy, I should just get the problem with 1 mark point on the outside and 1 on the inside, and that turns out to be this infinite polygon, which is one of the facets of this guy, the red facet. If I cut along one of these arcs, then the simplest case would be if I cut along a straight one, and again, that's just going to add 2 more points, and I should get a 5-point tree level or a pentagon. And you see, there's a pentagon, and all of these other guys are all pentagons. They're all interlaced with each other. They're all pentagons. But finally, we have this hole. We have this hole that would be there if we only had these variables that we knew and loved. But the hole is filled, and it looks like a hexagon here. Okay, and that hole exactly corresponds to this facet associated with this loop going around on the inside. And as I promised, what that's supposed to look like is what you get when you pinch on that surface. Well, when you pinch on that, on one side, you get a puncture in just 1 point. That gives you nothing. It's too small. But on the other side, you get a disk with 2 points on the outside and a puncture. Well, that's exactly a hexagon. That's what we saw a moment ago, is just a hexagon there. And that's exactly the hexagon that we see in this picture. Okay. All right. Now, in this case, this delta is, as I said, it's forced on us by the polytope. That the surfacehedron would have a hole without it. And it's qualitatively like gravity, and it has the qualitative property that we're used to again in string theory, where we discover closed strings in open string 1 loop scattering in the annulus diagram. But literally in this case, the canonical form associated with this polytope has a new pole with 1 over delta. The residue on that pole is a particular sort of entangled product of the forms associated with the 2 surfaces. And remember, what is delta? What would I associate with delta? The momentum I've associated with it is the sum of all these p's on the inside squared, which is exactly the momentum that you'd associate with a sort of closed string that would propagate between these guys. All right, so all of this flows just from this definition. All of this flows the really non-trivial thing that it's possible to choose these C's, which are all the equations are consistent with each other and that they're all positive. And then also demanding that all these X's are positive, as with the ABHY construction of the isosahedron, gives rise to these surfaces. All right, so the scattering form that's associated, the scattering form associated with all of these, with any surface. If I take that form and I pull it back onto the subspace that I just defined, where x plus y minus the sum over z's is a constant, this gives the trace phi cubed integrand. And once again, this is generally infinite because you would have infinitely many copies of the loop variables in the action of the mapping class. Okay? Now, what we were doing last year, when I was talking about this at the Amplitudes last year, even though we didn't know it in this language, but in the language we're talking about now, what we can do is adjust. I told you that we have to choose the C sort of carefully, to scale to infinity carefully, to die off an infinity carefully in such a way that the polytope is the infinite polytope is well defined. Well, we can just make a ton of them equal to 0. And if we make them 0, that collapses many of these sort of accordion infinite many facets, and we can end up having a finite number of them, and they can be naturally adjusted in such a way that we keep one copy of all the diagrams. See, this is a combinatorial problem, how to make sure you keep 1 or 2 or m copies of all the diagrams. We don't know the solution of the problem for totally general surfaces, but we know it in many examples. And we suspect that it's always generally possible to do. So as I said, this is like finding the fundamental domain for the integrand. But I'll come back to this later because there's another picture for what's going on where we actually get the actual amplitude, not just the integrand, the actual amplitude, where we won't need to do this. Again, there's new poles that are associated with these deltas that are something like gravity, and the projective invariance, that remarkable hidden symmetry of the forms, again, is totally manifest from the existence of the underlying pole. All right, so that's all I want to say about Surfacehedra by themselves. I now want to move on to talking about the binary geometries and amplitudes from the positive geometries rather than just integrands. But part of the motivation here, it's very closely connected to the story of the positive geometries and the canonical forms. After all, if we have a positive geometry, the way we associate an amplitude with it is to find the canonical form that has logarithmic singularities on the boundary. And for a general curvy positive geometry, in particular, like the n equals 4 Superyang-Mills amplituhedron, the big open question of the subject is there an invariant intrinsic way of computing this canonical form? The way that we talk about it for n equals 4 Superyang-Mills is one way or another give a triangulation in terms of simpler positive geometries, simpler cells, and then add up the form for all the simpler pieces to get that of the big object. That's not very satisfactory. First, it doesn't make it manifest that such an object even exists, the canonical form even exists, which is why the existence of canonical forms for amplituhedra is still mathematically conjectural, even though we believe that they exist physically, of course. And more importantly, it just doesn't give you an intrinsic definition, and not something you can just hand a computer mindlessly to go compute the canonical form. But when P is a polytope, we know two ways of giving a beautiful intrinsic definition. One of them is that the canonical form for a given for a polytope is an appropriately defined volume of the dual polytope. That's the earliest one that we knew, and then more recently, we have this intrinsic way of thinking about the canonical form for any polytope, but especially one, especially well suited to one which is naturally presented as the Minkowski sum of a bunch of simpler pieces, which is this notion of stringy canonical form. Okay, so if you have a polytope which is written as a Minkowski sum of simple pieces, and if I take each one of these simple pieces and I associate a polynomial with it, a polynomial whose vertices are integer points, or if I go backwards, if you give me a polynomial, then I can make it so-called Newton polytope, where the vertices of the Newton polytope are the exponent vectors of the variables in the polynomial. Then if I take weighted sums of those polytopes, then I get the canonical form for this weighted sum of the polytopes by this interesting integral, where I introduce a bunch of positive coordinates. So it's like I'm integrating over a simplex from 0 to infinity. In order to make this convergent, I have to make things convergent near x equals 0. So that's these factors, xi to the alpha prime, some variables capital Xi. And then I can make things convergent at infinity by multiplying by these polynomials raised to negative powers. Okay, so this is a natural object. It's a kind of a generalization of just the Euler beta function. And what we saw with Song and Thomas is that these things, as alpha prime goes to 0, reproduce the canonical form of the polytope. And sometimes at finite alpha prime, they have especially spectacular properties when the corresponding polytopes are associated with what we call binary geometry. So I will say a little bit more about that as we go. Now, this was actually a big motivation for thinking about, for spending so much time thinking about these trace phi cube theories, because there is a fantasy for a long time, and it continues to be a fantasy, that there is some picture for the n equals 4 super Yang-Mills amplitude that'll directly give us the canonical form. Since the earliest picture we had for these intrinsic definitions of canonical forms or in terms of dual volumes, the hope was for something like the dual of the amplitude, and that's still a fantasy. But since these surfacehedron polytopes are polytopes, then we know in principle how to think about their duals and how to write down these dual volume formulas for them. Okay. And again, more recently, again, just for polytopes, we have this stringy canonical form approach to extracting canonical forms. So we can try to see what both of these look like for surfacehedra. Okay, so what I'll talk about today is the second way, the binary geometries associated with the surfacehedra, which give us the stringy amplitudes. I won't talk about, but there's another story where we have the duals of these polytopes, and we can write down their dual volumes. And there's actually a beautiful way that turns out to be perfectly suited to this particular way of describing the polytopes that gives it totally concrete formulas, again, for the actual amplitude that connects to and generalizes the Feynman polytope picture that's associated with Schwinger parameter space and the semantic polynomials. In a very particular way, in a very concrete way, all the diagrams at some loop order can be unified into a single analog of a Schwinger parameter integral. It's not literally Schwinger parameters, but it's an analog of it, but not one diagram at a time, sort of putting them all together in one mass parameter. Anyway, I won't talk about this today, but I'll talk about the binary geometry and the stringy amplitudes. Maybe before we jump in, let me just say at least the structure of what I want to talk about. Then maybe we can take a tiny break and ask for questions. Associated with the surfacehedra, we're going to have binary geometries. What that means is that with every variable x, we're going to associate some u sub x, and there's another story here that connects these variables to hyperbolic geometry associated with these surfaces. So there's a whole story of looking at metrics of negative curvature on these two-dimensional surfaces. The space of all those metrics is Teichmuller space. And we can think about all these variables as ratios of certain geodesic lengths in this associated with the arcs in these constant negative curvature hyperbolic spaces. I won't talk about where that comes from. If we eventually get there after we clap, I'll talk about a more abstract way of thinking about what they are. But in any case, there's a way of associating with every arc on the surface a certain variable u. And then there's something utterly magical that these u's satisfy the following equation, that the u for any variable x plus the product over all y of uy to certain positive exponents is equal to 1. Okay? Now, this is the what we call the binary property back in 2019. See, what's remarkable about this is that this is a curvy surface which captures all of the compatibility and combinatorial properties of the surfacehedra polytopes that I was just telling you about. In particular, if you demand that all these u's are positive, then these equations tell you that they all also have to be less than 1, and these nxy are only non-zero when x and y on the surface intersect each other. Okay? So if they intersect each other, the corresponding propagators are not compatible. The arcs on the surface are not compatible. But you see, this surface is hardwiring that in. It says that if the u's are positive, then by these equations, they all also have to be less than 1. But if a given u for x goes to 0, then all the incompatible y's from this equation have to go to 1. So unlike these polytopes, which capture all of the compatibility information associated with curves on the surface, but still have some floppiness associated with them that's there in the choice of those constants, cxy, these binary things are completely locked. They're totally canonical. There's nothing you can do about them. The boundaries are zeros and ones. Okay? But these are highly nonlinear equations, and it's crazy that they're consistent. In fact, you see there's as many equations as there are unknowns. So naively, you would think that if they had solutions at all, they'll just be isolated points. They don't have isolated points of solutions. They have n-dimensional varieties as solutions. So the equations are highly non-trivially consistent with each other, and that non-triviality gets even more amazing in the infinite case, where there's infinitely many equations, and they're all compatible with each other. Okay, so it's this magical property that allows us to define stringy canonical forms associated with these guys, such that even at finite alpha prime, the factorization that we see at field theory is respected. The factorization properties of the integrand in the ordinary canonical form, in the alpha round goes to 0 limit, lift to something that continues to be true at finite alpha prime. That's a totally magical fact. Now, where does this magical fact come from? Well, this is what I alluded to before, that there's a fascinating, there's probably many ways of understanding it, but the one that I'm most entranced by right now, which I've also been learning from our mathematician friends in our collaboration, which is a certain structure in Quiver categories that underlie this magic. And as I mentioned right at the start, this is not just some blah, blah, blah. It practically directly hands us, instead of trying to solve these crazy equations, it directly hands us a parameterization of these equations of certain polynomials. We have an n-dimensional space and n variables, which remarkably satisfy these equations. And amongst other things, it also gives us a definition of the surfacehedra as a certain, again, in general, infinite Minkowski sum of the Newton polytopes associated with these polynomials. All right, so that's what I want to tell you about next. But perhaps we can take a little break and see if there are any questions right now.
Nima, can you hear me?
Yes.
Yeah, go ahead.
So you introduced, yes, the surfacehedra first in the context of biadjoint scalar theories. It was unclear to me if a surfacehedron corresponds to a single Feynman diagram contributing to the amplitude. No, it includes all of them, right?
Thanks for asking this question. Yes, no. If you give me a single trace phi cube diagram can also be thought of as giving me one triangulation of a surface. Okay. Now, what the surfacehedron is doing is giving you the contribution to the integrand from all the diagrams that have that particular that show up in that part of the genus expansion. So
the
role of one diagram is the same as the role of one triangulation, just specifying the surface. You want to specify which surface that I'm talking about? You give one triangulation, you give one diagram. It's the same thing.
And the fact that these, and you said these Surfacehedra are polytopes.
The Surfacehedra are polytopes. The Surfacehedra are polytopes. Now, what exactly the polytope? They always have the same. They always have the same combinatorics. They have the same facet structure, the same compatibilities. All those things are identical. What the literal polytope inequalities depend on what your choice of initial, triangulation. Okay. Even though all the combinatorics are the same, I mean, all the structure is the same, but the literal detailed inequalities that cut it out depend on your choice of initial triangulation.
And these are generically infinite because...
And they're generically infinite because they reflect the fact that once we start getting to the annulus and beyond, there is no, that while we have a canonical way of labeling loop momenta, that comes associated with homotopy classes of arcs. And since there's infinitely many arcs, we have infinitely many propagators, infinitely many copies of the same diagram. One way of thinking about it is take the annulus and take any given triangulation and take it and now take the inner annulus and just keep winding it. Okay, well, they're exactly the same at the level of the sort of what you'd associate with the Feynman diagram, but the labeling of the loop momenta changes from one diagram to the next. So the most natural object, if you don't do anything to it with no human intervention, the most natural object is infinite, and it has all those copies. As I said, you can do a human intervention to shut off all but finite number of the facets in such a way that you keep only one copy of all the diagrams. That's like that's like a choice of fundamental domain at the level of the integrand. Or we can do something different that I'll talk about in a moment.
Okay, so you will get back to this because you did allude to it later on.
Yeah.
It would be good if one could get at least systematically one definition of the integrand. Yes.
Well, as I said, there's a perfectly systematic definition of an infinite integrand. But you want something where you want a definition of a way of choosing a finite number of copies of all the Feynman diagrams.
Yes.
And that we know how to do in, for example, in this case of the annulus, we know how to do it. At two loops, we know how to do it. But yes, it would be good to have a sort of a combinatorial prescription for doing it in general.
Okay, thanks.
But as I said, in a moment, I'll be claiming that I'm going to be sidestepping that. In fact, you start seeing it on the screen right now.
Okay.
Any other questions?
Any further questions?
Okay, well, then maybe I'll just keep on going. Okay, so so now what we're going to do is, as I've said a number of times, you're going to associate a stringy canonical form with for any surface. And it looks like this. So I told you we have these U variables. The U variables can be expressed as ratios of polynomials and some positive variables little y. So I do it if I have an n-dimensional surfacehedron. I have alpha prime to the n. The integral over the positive region for the y's is d log y, and then the product of over all the chords ux to the alpha prime. And the exponent is just the p squared that's associated with the corresponding chord. All right, so that's what we've seen already in the story of stringy canonical forms, and also cluster polytopes at tree level and at one loop. We'll be talking about the one loop case in detail because, as I said, it's already sort of simpler and different than, importantly different than what we were talking about before. But what I want to point out already at this point, notice that all the dependence on the loop momenta that I see here is in this p squared of L. And since the p's are just linear in L, all the dependence on the loop momenta is quadratic in these exponents. And that means that just like we're used to with Schwinger parameterization, we can now, in this representation, we can trivially perform the Gaussian loop integral. Okay, so the dependence on L is just Gaussian, so we can do the loop integral. And after I do the loop integral, I'm left with this some integral dny, some function now where all the dependence on the loops are gone. So it's just a function of the external kinematic invariance and these y's. So effectively, I now have an integral over some parameterization of the space of curves on the surface, and some function of the external kinematic variables and these y's. Now comes the beautiful point, the obvious point that since everything that I did here, since everything that I started with was invariant, for example, in the case of the annulus, by taking the inner annulus and rotating it, that was the action of the mapping class group. That means that this whole object will be invariant under the action of the mapping class group. And that means that I get an artificial infinity when I do this loop integral. Okay? That infinity is precisely reflecting the artificial infinity in the integrand, okay, that we got infinitely many copies of the amplitude. So if I first got the integrand and then I tried to do the loop integral, I'd get infinity, but that's not what I'm doing. I'm representing the integrand as this stringy canonical form. Before doing the integral over the y's, I'm doing the loop integral, which is something perfectly finite. And finally, I'm doing the integral over the y's. Now I will have an artificial infinity because the thing that I'm integrating will be invariant under the action of the mapping class group. And therefore, to get something finite, I will simply, at this stage, mod out by the action of the mapping class group, and I'll get something perfectly finite. Okay, so this function, so in other words, all of the information about the binary geometry goes into these u's. From the u's, I get this function fs by doing the loop trivial Gaussian loop integral. And then finally, the infinity goes away when I'm integrating over the y's, I mod out by the action of the mapping class group to get something totally finite. Okay, I'll illustrate how this works in an example, but I just want to say what the general story is going to be. So in this way, we don't have to make any artificial human choices in how to regulate this polytope or thinking about it. The integrand is left alone as a sort of perfect object, and the amplitude itself is also its own natural perfect object, where the finiteness is just obtained by modding out by the action of the mapping class group at the end. All right, so now for the rest of this talk, I'll focus on what's going on at one loop in both the planar and the first simple non-planar example. And here we're going to, in the second example is where we're going to encounter this infinite integrand problem, and we'll see how the stringy integral naturally resolves. All right, but first let's talk about ordinary one loop. And if you were asleep for the last 50 minutes, you can wake up again because this is meant to be totally self-contained. You don't need to know anything about cluster algebras or polytope or any of that stuff. You can, I want to give a totally self-contained introduction to what's going on just at one loop, which already shows what a lot of the magic is. And then those few of you who might be around and interested later to see the more abstract, deeper origin of this magic from Quiver categories, you'll at least see what this structure is buying us. Okay, but let's first talk about what the variables are. So we're going to be talking about one loop, usual planar single trace one loop diagram. So first, let's talk about what all the variables are. So I have the loop variables that go from the outside to the puncture. And as I mentioned, there's two kinds that wind around one way and wind around the other. So I've just drawn one of them here. So that's y1 plus. I have these kind of variables between two boundaries. Okay, those are inner propagators. These are all various kinds of inner propagator. And I have this interesting loop-like variable that in a Feynman diagram are associated with tadpoles. So let me just show you what all these things look like in action. Let's say I take this triangulation. Okay, in this triangulation, that corresponds to this double line notation Feynman diagram, and that propagator in purple is that double line in the picture. Or if I take this diagram, okay, so this is the corresponding triangulation, and this guy, now see this guy is interesting because it goes between, if it didn't go around the puncture, if it went on this side, it would just be a sort of boundary arc, we wouldn't draw it, but it goes around the puncture, and that special feature is reflecting the fact that this is the internal part of a bubble on an external leg. And finally, the most extreme version of that phenomenon is when the loop comes in on itself, and that guy, so this is another triangulation, and that the green and the yellow and the purple propagators are shown in the corresponding Feynman diagram, and you see that this purple guy is associated, this purple loop guy is associated with the tadpole. Okay. So from now on, I'll just draw the triangulations of surfaces instead of the corresponding Feynman diagrams, but I hope you see what the corresponding. All right, so let's talk about what all of the diagrams would be. What are all the triangulations that we can have for for two external particles? So it would just be one loop bubble diagram. So it's what we call D2 hats. And let's just draw all of them. For example, I would start with this guy. That's the simplest triangulation. That's what would literally correspond to a bubble diagram, the Feynman diagram. But let's see what diagram can I draw that's whose propagators are compatible with the who are not compatible with this one. So for instance, I can take this guy here, this propagator, and it's not compatible with that loop from the top, because this loop from the top would intersect that guy. Okay, so there's this one, and then there's similarly the loop from the bottom here. Okay? Now that I have this guy, now who can I draw that's not compatible with the I just changed one line on this one. Of course, I can go back to where I came. But remember, the plus and the minus sort of are supposed to correspond to arcs that wind around many times one way or many times the other way. So clearly, those two things should not be allowed, would intersect each other many times on the surface. So I can flip from the plus to the minus, and then I can just repeat this story symmetrically on the other side. Okay, so these are 6 diagrams that I would have, and I have the plus and the minus propagators. Okay, and I have these, and I have the tadpole variables importantly as well. Okay, so the surfacehedron in this case is just combinatorially a hexagon, and this is different than what we talked about before in the context of cluster polytopes. So at one loop we have these cluster polytopes for D2, and D2 look like this. In fact, there was just A1 cross A1. The difference is that in D2, the plus and the minus variables that touch the same that come from the boundary and that come from the same boundary point and touch the puncture are to be treated as compatible with each other. And that's actually not natural. That's not natural from the perspective of the surface. From the perspective of the surface, it looks crazy because these are things that are highly incompatible. They're winding around oppositely around the puncture. They're intersecting each other a lot. So while it's a perfectly consistent thing to do, and there are good reasons for doing it from the cluster algebraist point of view, it's not natural from the point of view of Feynman diagrams and from the point of view of the surface. Okay? So this D2 hat rather than D2 is what we find more natural. So importantly, we are allowing having these variables that correspond to the tadpole propagators. Those were absent in this usual picture. Okay? And because of that, that means that not all of these things have good diagrammatic interpretations because they're missing the ones associated with tadpoles. Okay. All right. At least a clean interpretation of the ones associated with tadpoles.
Can I ask, Nima?
Yeah.
One more question in the previous slide.
Yes.
So the hexagon maybe D2, okay, say 1 cross A1, but D2 hat, at least topologically, it looks like a C2 or a B2 cluster.
No, it's not. That's actually coincidental. Yeah,
It's coincidental that the
yeah.
topology is.
Yes, yeah. Here it's topologically the same, but it's really not the same. Yeah, and you'll see the difference a little more clearly in the next example.
All right, thanks.
So okay, if we now go to a D3, so this is the previous one loop story we had, where coincidentally it looked like the three-dimensional isosahedron. So this is a picture of the three-dimensional isosahedron, except instead of cubic diagrams at tree level for 6 points, you have one loop diagrams for 3 external points. However, that's not what we get. That's not what D3 hat is. D3 hat is what you get when you take the equator of this picture and you blow it up into a belt. Okay, so you blow up everything, all these lines, into a little rectangle going around all the sides, and those are associated with a new facet. Okay, these are associated with new facets that importantly involve the tadpole diagrams. Okay, that were not captured in the same way correctly. Well, that were captured in a different way, but in an inconvenient way in D3. Okay, so D3 hat is different than D3. In fact, now I want to give you a picture for what these polytopes are. And in fact, a totally uniform picture for both tree level and one loop. Okay, so I want to give a simple picture for the origin of these polytopes. For this, I'm going to go back to something that we already saw at tree level, what we call the sort of a kinematic space-time picture for the tree level isosahedron. I'm going to revisit that picture and show that just 2 different ways of thinking about the wave equation in 1 + 1 dimensions, 2 different totally obvious ways of thinking about the wave equation in 1 + 1 dimensions, give rise to the 2 polytopes, the tree level isosahedron and this new DN hat. And so, and the structure is very simple and obvious without needing any background in thinking about the Dinkin diagrams associated with DN or anything like that. Okay, so this is a totally self-contained and simple thing. All right. So we're going to begin with thinking about the wave equation in 1 + 1 dimensions. And if you haven't seen this connection before, it might look like it's coming a little bit out of the blue, but this is, I hope, a story that's somewhat familiar from the Amplitudes talk 2 years ago. So we're going to take the wave equation in 1 + 1 dimensions, and we know that that if I work in terms of the light-like variables u and v, that the general solution of the wave equation is just some y plus of u plus y minus of v. All right, and now notice that the fact that there are 2 functions here, y plus and y minus, is reflecting, we know, the 2 degrees of freedom that we need in specifying the initial data, because this is a quadratic problem. Okay, so so here's a natural question. What are the natural ways of just presenting this initial data? Okay, so I just want to sort of graphically present this initial data, y plus of u and y minus of v. And one way of doing it, maybe one very obvious way of doing it, since u is a one light-like direction and v is the other light-like direction, is just draw 2 light-like directions. Okay, so here's some u direction, here's some v direction, and I'll specify this initial data just by giving the value of y plus here and of y minus there. Okay, and now if I do that, then my solution, then I can say that x out here somewhere at a random point is y plus of u plus y minus of v, and if I want, I can say it's minus the integral of some current that lives inside this rectangle. If I do that, if I add this current, then I will modify my equation so that du dv of x is equal to the current rather than just equal to a 0. Okay, So I'm going to slightly generalize to adding occurrence on the right-hand side. All right, so that's how I think about the solution of the wave equation if I give y plus and y minus on these two light-like directions. Now, let's say that I just want to give y plus. Well, then I need to put a boundary condition somewhere else in order to fix both y plus and y minus. So for instance, one thing that I can do is cap this whole thing off along a vertical line and just declare as a boundary condition that x equals 0 on that line. Okay, then if I do that, if you give me y plus, then I can determine y minus just by the fact that that 0 has got to equal y plus y minus the integral of the current inside this yellow rectangle. So that determines y minus in terms of y plus, or y plus in terms of y minus. Okay, so this is another way of specifying the initial data, where you just give me things along, let's say, the past boundary or the future boundary, together with this boundary condition that x equals 0. Okay, so that that's a continuous problem. Now we're going to discretize this problem. Instead of asking for the values of x, of u and v everywhere inside that diamond, we're going to take some discrete points and just shoot out light rays and bounce them off the boundaries of the space-time in the obvious way. Okay, so if I take on this past boundary a bunch of points, and now I'm just going to label them with the malice of foresight, 1, 3, 1, 4, 1, 5, 1, 6, let's say, and I just shoot the light rays out. Then I fill the inside in this discrete picture, and now I can solve for all the x's on the inside in terms of, let's say, x13, x14, and x15. Okay, so for instance, I can solve for x24 by as x14 plus x26. You see, I have x14 plus x26, or x24 is equal to x26 plus x14, and then I have the minus the total charge on the inside. So I associate some charge with this square or mesh C14 and with this square or mesh C15. I'm just using this general rule that we talked about here, that x is the y minus plus the y plus minus the total charge on the inside applied to this discrete case. All right, and you can think of the ABHY isosahedron as just specifying all the x's at this solution of the discretized wave equation and just asking them all to be positive, so long as the c's are also all positive. Okay. All right, so that's the ABHY isosahedron, and you can, having seen that, you can also ask another natural question. We know that when we think about the wave equation in the continuum, there's a natural notion of a Green's function, which is if you want to know what the solution looks like for a general source, you should work out what it looks like for a delta function source first. And then the general solution is the sum of what you get from delta functions in many places. Well, what's the discrete analog of that? Is I should shut off what the source is, what the c's are, in all of the squares but one. And if I do that, whatever space I get, so I get some polytope for general c's, but if I shut off all of them but a single one, that polytope is going to degenerate a lot. Okay? I can think of that as the response, as the polytope associated with a delta function source. And then the full polytope is just the sum of what I'd get by adding up over all those sources. In this case, the notion of sum is that of Minkowski's sum. And the Minkowski sum of A and B is just the most trivial thing. It's all the vectors that you get that are the form V in A plus W in B. Okay, so the notion of a Minkowski sum of polytopes is just the dumbest way of adding of two polytopes you could imagine, even just any two sets. Okay, so it's natural then to ask what you get when you shut off all of these sources except in one of these meshes. And quite beautifully, what you discover is that what you get if you shut off all but a single mesh is that the whole polytope collapses to a simplex. And now I'm conveniently representing what that simplex is by just giving you a polynomial where, for example, if I have 1 plus y1, this this is a simplex whose vertices are just given by the exponent vectors of what I get in the in this polynomial. So in this case, there'll just be an interval between the origin and the y1 axis, the point 1 on the y1 axis. This guy would be a triangle with an origin and a point on the y2 equals 1, and then a point at y1 and y2 equals 1, and so on. And so each one of these, what I get when I just turn on the source in one of these meshes and shut off everything everywhere else is a simplex, and it's these particular simple, especially simple simplices. All right, so just keep that in mind. All right, now let's go back to the continuum wave equation. And let's think about another way of specifying the initial data. And this is in many ways an even better way of specifying the initial data, a more obvious way, a more Newtonian way, which is you just imagine giving the data on a spatial slice. Okay, and what do we normally do? We give the data on a spatial slice, and we give the initial x and x dot, right? The initial position and velocity. Well, here I'm thinking in terms of y plus of u and y minus of v. So what I'm going to do is just give the information of y plus of u as a function of u. It's just one function on this slice, and y minus as another function on this slice. Okay. And now what am I going to do for x? Well, x at a given point up here, u of v is again going to be y left here at this corner plus y right at this corner. So I'm going to call it x is y left plus y right minus the sum of the charge in this triangle. Okay. Okay, so this is another way of specifying the initial data associated with the wave equation. And just as before, if I want to just specify y plus or y minus, or just y of u or y minus of v, I can also give a boundary condition somewhere else. So in this case, I can put another point up here, x equals 0, and just say x equals 0 up there. And once again, this will relate y plus down at this point to y minus at the next point over. Okay, so if this distance here is L, it'll relate y plus an x to y minus an x plus 2L. And so you see the whole picture is naturally periodic in the horizontal direction. Okay. So once again, I can give either y plus or y minus as initial data. Now, exactly as before, I can discretize and shoot out light rays. So let's imagine I discretize the place I'm giving my initial data. Here it is. And I'm going to shoot out light rays. And so I'm going to now make this kind of grid. And you'll notice that in this grid, all the squares up here, everything is supposed to be 0. Okay, that's my future boundary there. And all the grids look the same, except I have the little ones that look like triangles down there. And again, I'm going to give my solution of the discrete wave equation now as being that x at any given point is the y left plus y right minus plus the sum of all of these of the constants that I would associate with each one of these things, including the ones associated with the triangles down there. Okay. Now, amazingly, if you now just look at the variables that we get in this picture, importantly, including the sort of difference that there are some guys right at the very bottom here who are different than the rest, because they're associated with these little triangles rather than with the squares. Just the variables in this picture are naturally in one-to-one correspondence with the chords of dn hat. For example, I could label here, this would be 1, 3, 1, 4, and then this would be for n equals 4. So 1, 3, 1, 4 is going around, and it comes back 1, 1 would be the like self-loop variable. Okay. And then the ones at the bottom are just there's a y plus and a y minus, and it's just convenient to label them as y plus j and y minus j minus 1, and the whole picture again is just cyclically rotated as we go in this direction. So the whole thing is periodic in the horizontal direction. All right. So the labels we see of the vertices in this picture are exactly the ones that we can associate with the variables of dn hat. And the claim is that if you just demand that you have a solution of that you solve for all these x's inside, you demand that they're all positive when all these mesh constants are positive, that gives you another polytope. It's not the icosahedron, but it's the polytope for dn hat. Not dn, but for dn hat. And just as before, we can ask for this sort of Green's function picture to see what was interesting in the case of the tree level is that the sort of complicated polytope could be built out of the Minkowski sum of these extremely simple pieces. And that's the analog of the Green's function picture for the polytope. Well, the same thing is true here. Exactly the same thing is true here. We can again ask what are the individual building blocks that we get when we shut off all of the constants except one. And once again, they're all simplices, and there are these very simple objects. For example, the one associated with this would be a simplex 0 less than y3, y3 between 0 and 1, so it'd be an interval. The next one over would be y3 less than y4, sandwiched between 0 and 1, and so on. Okay? So all of these are again associated with simplices, and I could group them into a polynomial again in exactly the way that that we saw before. And here are the polynomials that we see. So something between I and j that reflects the following ordered simplex between 0 and 1. And here's the notation that we'll see in the rest of the talk for that particular polynomial associated with that simplex. Okay, so that's dn hat. So you see that it's just another way of thinking about the wave equation in 1 + 1 dimensions. One way gives us the tree level icosahedron, and this other way gives us the one loop surfacehedron. Okay. Now, what we can do at both tree level and at one loop, but let me jump ahead now to what we do at one loop. Beginning with these polynomials, we can write down a stringy canonical form, where the polynomials that occur in the stringy canonical form are exactly these polynomials, exactly the polynomials that we see associated with these little Minkowski summations. And simply doing that defines what the u variables are. Okay? So that gives us a definition of what the u variables are. And so here's what they are for dn hat in general. And you can then check remarkably that these things satisfy these binary equations, so that u for x plus the product of y, uy to the nxy is equal to 1, where this nxy is literally the number of times that the corresponding curves x and y intersect each other on the surface. For example, here is concretely what they are for d2 hat. Okay, so here are what all the variables are, plus their cyclic images, and you can just check that they satisfy these equations, where, for instance, in this case, you see some powers of 2, because 1, 1 and 2, 2, those curves intersect each other twice. Okay, so we see a power of 2 in the exponent there. All right. So, okay, now, so those are the u variables for dn hat. Let's now move on to talking about what the actual stringy forms are. Well, at tree level, we can do exactly the same thing. We get the u variables at tree level. They satisfy the same structure formula, except now all these exponents are equal to 1. And as I alluded to already, the remarkable fact about these binary geometries is that when ux goes to 0, all the incompatible ones go to 1. And that means that this integral develops singularities when some of the u's go to 0. But because all the other u's go to 1, the singularities are factorized in exactly the same way at finite alpha prime that they did at alpha prime goes to 0. And in particular, the singularities even at finite alpha prime reflect the cutting and pinching of the surface, not just at alpha prime equals 0, but at any alpha prime. Okay? And this, of course, is the Kobe-Nielsen, essentially the Kobe-Nielsen amplitude at tree level. And we sometimes loosely call this the Kobe-Nielsen amplitude, at least I do. But of course, it's not directly related to a known string background, i.e. with massive trace phi cube scalars rather than gluons. But I do want to make a little comment that if I thought of this as a physical amplitude for scalars, it's not garbage. I mean, obviously, it's the usual beta function formula, but it's not the Veneziano amplitude for tachyons, not an amplitude for gluons, but it does have positive unitary residues on the poles for all d less than or equal to 10. So at least it's not space-time dimensions less than or equal to 10, just like the open superstring. So at least it's not immediately dead as a physical theory. Okay. All right, now let's move on to one loop. So we're going to, now that we know our surfacehedron is dn hat, we have u variables for it. So again, we're going to define these stringy canonical forms. No, we still don't have this business about the infinity and the windings and all that. That's going to start at the annulus. This is still just that one loop with just a puncture, so we don't have that yet. So I'm going to spend some time talking about some of the novelties in this case. So here it is, exactly the same structure. I have the uij to the xij, and then I have the u's for the loop variables, the y. And I have a separate one for y plus and a y minus. And as I mentioned, these satisfy the binary equation. So again, the integrand will perfectly reflect the factorization at finite alpha prime. But now, as I mentioned on general grounds in the beginning, where is the dependence on the loop momentum? It's just there in the y. All the y's are just equal to L plus some sum of p's all squared. So we can just do the loop integral as a Gaussian integral and be left with just an n-dimensional integral over the variables associated with this n-dimensional moduli space. So let's make a sort of first comparison with what we might expect in string theory. It looks like I'm talking about a diagram with a puncture in it. Okay, so it looks like I'm talking about I'd be talking about this sort of worldsheet diagram, but this worldsheet in moduli space is n-1 dimension. Okay, so if you fix the point, the puncture to the origin, mod out by the residual symmetry, it's an n-1 dimensional integral, while our integral is n dimensional. So that's actually the one first point, is that we should really be thinking about our integral, our object. That puncture in the middle is really a little hole. Okay? It's really a little hole with no marked point on the inside, and there's one extra variable associated with the size of that hole. If you want to think about it in the standard stringy point of view, we're not thinking about it in that way. I'll come back to that point in a second. But if we just want to match the dimensions, the thing that we're really computing is meant to be compared with this diagram in string theory, not this one. Okay? And that's actually good, because this is what we'd associate with just the pure gluon amplitude on the outside. This is what we'd associate with also emitting a closed string. Okay? We'll talk about the relation between those two things in just a moment. All right? Okay. Now, let's look at the very simplest thing that we can do. Is just the tadpole. Okay, so this would be d1 hat, the dumbest thing in the world, d1 hat. Here's an interesting difference, another interesting difference in string theory, especially non-supersymmetric string theories have tadpoles up the wazoo, right? They have tadpoles and infrared divergence associated with tadpole emission all over the place without supersymmetry. And actually, so would we. So would we if we literally followed the rule that said that we'll associate to every arc the momentum associated with that arc. So if I literally followed that rule here, then I would assign the momentum 0 to this arc, because the homology associated with it would give me momentum 0, exactly what we just expect with the field theory diagram. However, I can totally consistently, in defining my integrals, instead of putting 0 there, just associate a particular I can associate there's no variable. Ignore what I said in this example. It'll be relevant in a future example, because we don't actually have there's no variable associated with that propagator here. This guy is just this propagator. Okay, so sorry, ignore what I just said about that. But one thing that I can do is I can put in just to have some control. If I do nothing else and it's just a trace by cube theory, I just get a number from doing this integral. But I can put in a mass. I can put a mass for the scalar running around on the inside. Okay, So if I did this in the field theory limit, I would just get the integral ddl over L squared plus M squared is some UV divergent thing. But now for us, D1 hat, I mean, the form is just the usual trivial interval. So we just get this du over u of 1 minus u. So this is what I get, a u to the y, 1 minus u to the y plus and a y minus. Those are my two kinds of tagged and untagged variables. But now, what momenta should I associate with those variables? Well, the tagged and the untagged, I'm just going to give them the same momentum, obviously. They're related by this obvious symmetry. So we'll just give them exactly the same momentum, but I'll add a mass just so I have a function of something to look at. All right. So that's the integrand that I would get. As alpha prime goes to 0, it would just get me 1 over L squared plus M squared. But now I can do the loop integral. Okay, now I can do the integral ddl. I just do the Gaussian integral, and this is what I'm left with. Okay? So now I have a function that depends on M squared. And two comments. So you see it's an interesting integrand. Before I used to just have this rational thing in the integrand, this du over u1 minus u. Now I have this stuff with a logarithm in it. But just two qualitative comments about it. First, it's totally UV finite. So the divergence in the field theory is gone, it's cured by alpha prime. And secondly, it's exponentially damped for large M squared, which is again manifest because these u's are between 0 and 1. So for large M squared, this is exponentially damped. Okay, so this is our first peek into what happens at high energy in these amplitudes that they're exponentially damped. Now, in fact, we can give a general formula for this, again, this is the amplitude now. We're going to do the loop integral. So for the actual amplitude, what do? We take xij, we're going to equate the xij and the xji and set them all equal to the corresponding sum of momenta. If I use dual variables, I'd write them as xi minus xj squared. For the adjacent xii plus 1, these would be associated with the external line bubbles. Again, naively, I put a 0 there, but once again, I can control that. And I can just say, well, there's some mass normalization, so I'll just call xii plus 1 M squared and say it's a common M squared for everybody. And finally, now the comment I was making before about the tadpoles is relevant. Now all the objects xii, which would be associated with these tadpoles, I'm also going to, instead of saying that they're 0 and getting a divergence associated with them, I'm going to just give them all also a name, and I'm going to call them T. Okay, so we can sort of regulate the mass renormalization and the tadpole just by giving the corresponding propagated variables names. And finally, the loop variables, again, the plus and the minus loop variables will be identified, and again, in dual coordinates, it'll be some x naught minus xi squared, and we'll integrate over x naught. And this is the final result. So it depends on the external Mandelstam invariance, the xij, as well as a bunch of other parameters. I added these just so we see the most general thing. I added the mass normalization for the bubbles on the external legs, the tadpoles, as well as an internal mass for the scalars. And so so the loop momenta are gone. We have this n-dimensional integral over the space left. All the dependence on the Mandelstam invariance is in this interesting combination here. There's the stuff that depends on the tadpoles and the bubble and the internal masses, and then the juicy part I get from doing the Gaussian integral, which gives me an additional dependence on the Mandelstam invariance in there. Okay. So this is some interesting new representation of the one loop amplitude as an n-dimensional integral. It's a little bit like Schwinger parameter, definitely not exactly. Schwinger parameter for one diagram at one loop would give you an n-1 dimensional integral. This is an n-dimensional integral, so it's one more variable, but it's summing over all the diagrams together in one unified object. And again, the loop momenta are gone, of course. We've done the loop, of course, it's the actual integral. So what's the qualitative structure? Well, we know that at tree level, we get some n-3 dimensional integral, and we get this u to the alpha prime x. So the singularities here, which occur as u goes to 0, gives me something rational as alpha prime goes to 0. But at one loop, here I get u to the, you see, from this expression that I get from the Gaussian integral, I get something that looks like u to the log u. So it's qualitatively u to the log u. As u goes to 0, I will get things that are modulated by logs and polylogs and things that have branch cuts. That's where the branch cuts of the loop amplitudes occur in the field theory limit as alpha prime goes. Okay, so here's just to concretely see for the special case of 4-point scattering. This is what the whole answer looks like. It's a function of s and t, as well as all these external things from the tadpoles and the mass normalization and the internal mass. And all of these expressions are explicitly given. They're just logarithms of ratios of polynomials in terms of those y variables. Okay? So if you're familiar with the stringy one-loop integrals, there's nothing elliptic in sight here. We don't see any taus, we don't see modular prime, we don't see anything like that. Instead, we have these integrals involving these exponentials of logarithms of ratios of polynomials in these variables. So it's a very different looking representation. Nonetheless, it's guaranteed that as alpha prime goes to 0, this matches the field theory limit, regulated in the UV by alpha prime in some way. Okay, so at the very least, what these things are a new kind of ultraviolet regularization of field theory amplitudes, and especially amplitudes as an integral over the corresponding binary positive spaces. Okay, but obviously, since at tree level we got string amplitudes, we want to know what are we actually getting here at loop level. What is the high energy behavior of this keeping alpha prime fixed? So it's obvious we get UV finiteness in any number of dimensions. It's also obvious that there's part of the kinematic space which corresponds to the positive region in 2-2 signature that we usually talk about in this business, where everything again is trivially exponentially small because of all the exponents in these integrals are positive, and what we're integrating are numbers between 0 and 1 raised to large positive powers. But what happens for 3-1 signature for physical high energy scattering at fixed angle? And we're right now, really busy trying to understand the analytic structure of these objects more generally, and also so we can do the discontinuity analysis and check for unitarity at loop level and so on. But just to get an idea of the high energy behavior, it's easy to do a saddle point analysis. And let me remind you how that saddle point analysis for high energy scattering works at tree level. In the language of these U variables, the action that we talk about, the logarithm of the integrand is just the sum of xij log uij. And the critical points of this are the Gross-Mendel equations of the scattering equations. Now we know these guys have n-3 factorial solutions, but if you look in the physical region, high energy fixed angle, and I don't know actually a proof of this fact, but it's observationally true, certainly at 4 points and 5 points, that all the saddles have negative action at high energy and fixed angle. Okay, so you get exponentially small amplitudes. Now, this is not true if you make, let's say, S large and positive and T negative, but make the magnitude of negative T bigger than S. That would not correspond to a physical scattering angle, and that is indeed one of the places where the string amplitudes blow up exponentially. But when you're in the physical region, they die exponentially, and that's, I think, quite an interesting thing, and not sort of manifest from the inspection of the scattering equations, especially at higher points, why that should be true, but it appears to be the case. Okay, so we can do a similar analysis for us at one loop. I'm going to define this sort of composite object, capital Uij, which is just the product of the little u's for the ij going one way and the other way around the aperture. So that's a natural object that shows up. And it turns out that despite the fact that this integral looks a little bit scary, that all the stuff in here is irrelevant for the saddle point analysis. Okay, so that everything just boils down to this part. And here is just that composite that I just defined, the product of the Uij and the Uji. So we have a new set of scattering equations with a new set of u's. And again, I can look at the saddle points. Here is very concretely what they are at 4 points. It's just S log U13 plus T log U24. Here are the U's. And I can just shove that in, look at the saddle points. And now the saddle points, there are 3 saddles, but amazingly, for a high energy fixed angle, all 3 have negative action. So it doesn't matter, you don't have to make an argument about which one is chosen, how you deform the contour, whatever is going on, all of them have negative action. And therefore the high energy amplitude at fixed angle is again exponentially suppressed. This is not true. It's again not true if the magnitude of T over S is bigger than 1, but it's exponentially suppressed literally in the physical region, just like physical string theory. Okay, I want to make one last point about dn hat, which is that in this object that we talked about, there's no boundary in the geometry that, I remember I told you we should really be thinking about what we're doing if we're comparing to the usual world sheet as an annulus with no marked points on the inside. But in our story, there's no boundary or no singularity associated with this internal guy shrinking to 0. However, there's a natural way of, there's a natural thing that we can do to our story at the level of the polytope, which is motivated by this funny observation that we had these plus and the minus variables. Remember, the plus winding and the minus winding variables. If we go back to this picture of the actual polytope, it has a plane of symmetry where all the plus guys are on one side and the minus guys are on the other side. Okay? So since that's the case, it's natural to slice this guy in half. And that's what we did already talked about in our 2019 work, where we talked about cluster polytopes for dn, is we define what we call dn bar by slicing the guy in half. Okay, well, we can do exactly the same thing now with dn hat. We can take dn hat and we can slice it in half. And if we do that, we make a new facet, okay? And this new facet, just as was the case for the dn bar story, this new facet is a very nice interpretation, as all the vertices on that facet are associated with diagrams where you knit a tadpole off all possible lengths. So they're all the tadpole diagrams. That's the thing to the cognoscenti that's associated with the Bn-1 or the Cn-1 cyclohedron cluster polytopes. All right. But a beautiful thing is that this full polytope, dn hat cut in half, this is something that already exists. It's called the halohedron, and it's what Giulio Salvatore very early on proposed as being related to the amplitudes at one loop. Okay, so now the halohedron fits in to this whole story. The halohedron is what we get if we take the surfacehedron and we chop it in half. But also quite beautifully, the halohedron has an effective binary realization. That's because it turns out when you look at the u variables have the beautiful property that if the u variables for y plus, for any one of the y pluses, like let's say y1 plus is bigger than that for y1 minus, all of them are bigger. So the U space itself is broken up into 2 regions where all the U's for the pluses are bigger than the minuses and the other way around. And so that means that we can chop U space in half. And once we do that, there is a new boundary. It's extremely simple to see that the ratio of these 2 U's, it crosses between bigger than 1 and less than 1, depending only on whether the product of all these Y variables that went into defining the polynomials defining these U's, whether the product of all the Y variables is bigger than 1 or less than 1. So chopping the space in 2 means at the level of the binary geometry that I have to integrate now not only over all the Y's, but all the Y's or the product is bigger than 1. And instead of integrating the form that has singularities only at y equals 0 and infinity, it also has to have a logarithmic singularity on this new boundary that I added. Okay. But then apart from that, I again just have the product of all the U variables raised to their power, as well as as something new associated with this new boundary that I added, which I precisely associate with this new tadpole facet. This guy now has a new pole as t goes to 0. This is interpreted as a new singularity as the internal annulus shrinks to 0 size. And this is what's very reminiscent of the closed string tadpole emission that we get. And in particular, the residue is what the residue corresponds to the form on this T facet, And what is that? That looks precisely like the emission of a tadpole, which we think of as a tree-level closed string emission off of this one-loop tree-level open string process. Okay. All right. So, all right. So that's all I want to say about the planar one-loop case. Now let me make a few comments about the double trace case. So I'm going to look at the simplest case of the bubble again, but so this is what the Feynman diagram looks like. This is the corresponding surface. And there are, I won't go through it in a detail. We begin life with a simple set of variables that are naturally associated with hyperbolic lengths in this geometry. But there's both for the ordinary variables as well as this delta variable, the circle, the closed loop going around the outside. There's a very natural change of variables from these variables to some new ones that I'll call little delta and t. I've written them explicitly here. The action of the mapping class group is just clocking over the xj's by 1, and in these new variables, it just shifts t by delta. Okay, so the action of the mapping class group is just t goes to t plus delta, and also the canonical form that we want to integrate, this d log x naught d log x1, just turns into dt d delta. All right, we can then make, and this is where the slightly artisanal part of the story comes in. We don't know more systematically where any of this comes from, but there's in these cases, there's a very obvious guess for what the u variables should be corresponding to the ordinary arcs. I won't go through it in detail, but this is the first thing you would write down if you followed any of our previous story. And you can write this in terms of these new variables, these t's and deltas, in a very simple way. But already something interesting happens. If you take the product over all of these u variables, you find there's a telescopic cancellation of this product, but it goes to a fixed finite thing. It goes to this e to the negative delta, where delta is the variable, is this variable that controls the sort of length of this capital delta closed string loop. And then if I look at what the ersatz u equation should be, I would take, let's say, the variable x naught, and then I would write down the product of the u's raised to the power of the number of times the new variables intersect x naught. So I would get this huge infinite, I get this infinite product in two directions with u1. The next curve intersects it twice, so I get u2 squared. The next curve intersects it 3 times, I get u3 cubed, and so on. So I get a big infinite product here, I get a big infinite product there. And you can just ask, is that equal to 1? And it isn't equal to 1. Too bad. But you see, is it off by something simple? And amazingly, it's off just by this tiny, simple extra factor. So in fact, there are an extended set of u equations, but you have to see the u variables for other things that are not just the obvious chords that you had to begin with, but which also involve delta. And here are what the u equations are. They're exactly what I said, but there's one more factor, which is this u delta squared. Now, why is that power 2? Quite mysterious right now. That's one of the things. Anyway, well, but it's squared, and this u delta you're to think of as a u associated with these loops that just go around, and so they are incompatible with all the other arcs that cross them. So you'd expect an equation like u plus the product of all these u's is equal to 1. And that's, in fact, exactly correct. Because the product of all these u's ends up precisely being that e to the minus 2 delta, as I told you. So this bottom equation solves for u delta is equal to 1 minus that product. And that's exactly what we were off by in the previous equation for the top line. Okay, so first of all, there's this infinite set of equations which capture the binary geometry. Amazingly, the binary geometry knows by itself that it's incomplete. It needs this extra business with delta, just like the surfacehedron itself knew that it was incomplete and it needed this extra business with delta to be completed. But not only do we have these infinite set of nonlinear equations, we also have a solution to the infinite set of equations, parametrized in terms of t and delta in this particular way. All right, so now we can go off and do the integral, exactly the same as before. Now we're going to associate with every one of these arcs going around j times. Well, we said, what is the loop momentum associated with this? It's L plus Pj, where P is the total momentum coming in from the inner annulus here. Okay, so I'm going to say that this xj is L plus Pj all squared plus m squared. And so here is the integral. Okay, I'd have to integrate over delta and t of just dt d delta. Remember, that was the d log form. And then just the product of uj to the alpha prime L plus Pj squared plus m squared. And also I could add a factor of u delta to the power of its corresponding delta. I left that out here for the moment. I want to point out here that if I do this, and if I take the alpha prime goes to zero limit, what I'll get from this is the infinite form. I would get the infinite form where I sum over the diagrams with the loop momenta shifted by Pj as I go. So that's the infinitely many copies of the diagrams that we talked about. But as I said, on general ground, so if we take the alpha prime goes to zero limit, or let's say we get the stringy form and then we integrate over the loop momenta, we'll get infinity. So let's do it the other way around. We'll integrate over the loop momentum first, but that's trivial because it's a Gaussian integral. Okay, so and what we're going to get is an integral dt d delta, some function of t and delta, but this is guaranteed to be mapping class group invariant. So it'll satisfy that f of t plus delta is equal to f of t. And therefore, this integral is going to stupidly give us an infinity, just because it's counting that infinitely many times. So what we should do is mod out by the mapping class group, which trivially in this case just means that I do the integral from minus delta half to delta half, let's say, any fundamental domain that I like. This now is going to give me a completely finite amplitude, and this infinite overcounting issue is all gone. All right. And here is concretely what we get. So we get, again, from the Gaussian integral, we get something that looks like an exponential of a log of u's. This looks like a slightly scary expression, but perhaps analytically and certainly numerically, it's astonishingly close to this very simple approximation. So if we take this very simple approximation, we get a very simple form for the integrand that we're now supposed to integrate over t and delta. And now when we do the integral, now you see that everything is regulated. Alpha prime regulates everything. And in 4 dimensions, for example, if I forget about this power of u delta for the moment, so I just look at the dependence on the usual p squared for the bubble, then you can easily see that as alpha prime goes to the limit, this gives you log alpha prime p squared. That's exactly what you'd expect from the bubble. And it's ultraviolet finite. Again, it's cut off by alpha prime. So there's no infinity, there's no spurious counting, all that's gone, and we reproduce what you'd expect from the low energy field theory cut off by alpha prime. In general dimension, if I now take the opposite limit where I forget about the dependence on the external momenta, but I keep track of the dependence on the power of delta, of u delta, then I get an interesting expression of those poles in this variable. An infinite series of poles that I can really think of as closed string poles. And amusingly, it's actually massless and d equals 4. And we're trying to figure out with the analytic structure how to think about these objects in general, where you turn everything on, and to really see what the analytic structure is. As I said, both even in the earlier one loop example as well as this example, to try to understand whether we can do the analytic continuation into the physical region well enough to control the discontinuity across the branch cut and check for physical unitarity. That's something else that we're in the middle of looking at now. So don't have anything to say about that yet, but at least at first blush, we have integrals that are ultraviolet finite, exponentially soft in the obvious positive 2-2 positive regime, more remarkably exponentially soft in the physical high energy fixed angle scattering limit, and which and certainly give us an ultraviolet regulation of the low energy field theory. I want to make a final comment, something else that we're looking at. I keep telling you that these deltas are supposed to be associated with gravity somehow. And so if we really put our money where our mouth is, we would expect the following thing. If I'm talking about at the level of the integrand, then there are poles associated with these deltas, as I said, but the factorization on those poles has some interesting features associated with it. It's not the most obvious direct multiplicative factorization. It's what we call entangled factorization. It's a very specific kind of factorization at the level of the polytope, where you get the product of the two lower polytopes, but it's projected down to a lower surface. And that fact that it's not exactly factorization means that to see something closer to exact factorization, you have to go down not just in dimension 1, but in dimension 2. And that's again something that looks correct from the interpretation of where you see the singularities for closed string scattering. We have 4-point closed string scattering. The singularities are not seen when we integrate over moduli space. They're not seen in codimension 1, but they're seen in codimension 2, real codimension 2, where you get the long skinny tube connecting two spheres. But we would think that if this connection is there, if we actually do the loop integrals to get the amplitude and not just the integrand, then we should get an object that depends on deltas, and perhaps that object has some resemblance to gravity amplitudes. Or again, there's no polarization here, so it's a scalar avatar of gravity amplitudes, which means something that's totally permutation invariant, no color, and so on. So we can begin, for example, by looking at the 3-punctured sphere. Okay, so we have the 3-punctured sphere as a trace by cube diagram. As a trace by cube thing, this would just correspond to some 2-loop vacuum graphs. So if we just do the 2-loop integrals at finite alpha prime, we just get some number here. Okay, so that's fine. We can dually think about this as a 3-graviton, quote unquote 3-graviton amplitude. That should just be a number. Now, if we go to the 4-punctured sphere, now again, this is some 3-loop vacuum graph as a trace by cube theory. So if we do the integral of the loop momenta, we're just left with the dependence on the deltas. And now the deltas are, there's a delta for S, for T, and for U, and actually all the other deltas with more complicated surfaces are homologous to these. So these are the only deltas that we have, which give us a good parameterization of the STU kinematics, and also homologically the sum of these curves is indeed equal to 0, which is S plus T plus U equals 0. So we get some function of the deltas after we do these loop integrals. What is that function? Could it be that we get something that looks like Virasoro-Shapiro amplitude out of this? We don't know. That's something that we're looking at. Clearly has singularities. It has singularities corresponding to these pinchings, but exactly the structure, what it looks like, and so on, we don't yet know. But in principle, this is a way of associating the variables that we would associate with gravity amplitudes, some way of extracting them from this binary geometry and doing the loop integrals. Again, all these loop integrals are just trivial Gaussian integrals. We're just left with an integral over these y variables that are associated with the corresponding. All right, so that's all I wanted to say about this one loop story, and I just want to end with the totally obvious question that I hope I have turned into a burning one in your mind. It's certainly what's preoccupying us now. What the hell are these stringy amplitudes? They're very naturally defined, associated with these surfaces. They have all these qualitative properties in common with string amplitudes. What are they? Are they a new kind of string theory? I think it's more likely that some new view of what string theory is, some new way of thinking about amplitudes in string theory. Note that there's no worldsheet, no CFT. Just practically speaking, there's no elliptic functions or anything at one loop. Okay, so another difference, so far we've seen no critical dimension, we've seen no infinities associated with the bubbles and the tadpoles, or they are there, but we can control them just by putting in variables associated with the bubbles and the tadpoles. So these are all things that are not quite the same as ordinary string theory. And obviously it's not going to be literally some actual string background, because we don't know an actual non-supersymmetric string background that gives us this trace by cube thing. But it could be that it's related to some way of parametrizing the moduli space from a very different point of view, and connecting to string theory in that way. A huge question in this business, going all the way back to tree level, is somehow the trace phi cube structure is all about the universal factorizations that we have at long distances for any theory. But we know that the real physics we care about has polarization vectors for Yang-Mills and for gravity. So the question is not only how can we add polarization to this sort of positive geometric way of thinking about this physics, but what's the raison d'etre of polarization vectors from this point of view? Why do we need them? Why are they forced on us in some way? That we don't yet know. But clearly we need something to understand that question all the way back at tree level, even in order to see whether literally getting Yang-Mills and maybe even real gravity out of this might happen. Let me just sort of end by mentioning why it's not trivial to compare this with ordinary string theory and what the sort of conceptual differences. And it really boils down to the fact that we have very different views of the Teichmuller space or the moduli space that we're used to thinking about when we do string integrals. Let's do a really simple example of this bubble diagram, okay? In conventional string theory, there's a two-dimensional moduli space in here, okay? And I have 2 points on the outside and this little circle with some size r. It's a two-dimensional moduli space, and the standard way of parameterizing this, if you're a worldsheet person, would be in terms of the radius of this little annulus and the angle around the outside. Okay, so this is the sort of r theta way of thinking about the worldsheet. And where does this come from? It comes from the fact that in the standard way of thinking about string theory, we think about the worldsheet metric in a totally local way. We really imagine there's a metric at every point on the worldsheet up to Weil rescaling, and that's what we think about. On the other hand, our way of thinking about the moduli space or the Teichmuller space, and this is the connection between all the things that we're talking about in hyperbolic geometry that I've said nothing about, but which you can look at some of Giulio's lovely talks at recent meetings where he spent a little bit more time talking about this. But basically, you know, our variables are these arcs, and we think about the geometry of the surface not by giving the metric locally on the surface, but by specifying all these geodesic lengths of all these arcs. So it's a more global way of thinking about it. We don't have a local access to the metric on the worldsheet. We have a global access via specifying the lengths of all these geodesics. So they're both two-dimensional moduli spaces, but there's a very non-trivial mapping between these two sets of variables. And I actually very highly doubt, I mean, you can in principle write it down, but we certainly don't know any practical map between these two sets of variables. And it's furthermore highly unlikely that even though such a map existed, you would just take that map, shove it into the usual string integrand, and out would pop this one. They're very unlikely to be the same as each other, but they may well be the same up to total derivatives. Okay, so this is very likely just a very different way of thinking about the integral over the moduli space. From this point of view of thinking about the geodesics on the surface rather than locally thinking in terms of the metrics on the surface. And that has another consequence, which is as alpha prime goes to 0, what the usual worldsheet picture lands on is the world line formalism. And as alpha prime goes to 0, the picture that the string is unifying everything gets broken up into individual Feynman diagrams for different processes. Okay, that's the world line picture. But that's not what we get. Our picture, as alpha prime goes to 0, lands us on the canonical form of the surfacehedron. You see, the surfacehedron already is doing something stringy, even at alpha prime goes to 0. Even at alpha prime goes to 0, it's a master object that unifies all the diagrams together in one big thing. Okay, so it still sees them all unified. And this is matching not to the world line picture of physics, but to the field theory picture of the physics. Most obviously seen in the fact that we can naturally, if we don't do the loop integrals, we can actually naturally land on an integrand. And that's the sort of starting point to something that looks like the integrand. That's the starting point that's naturally associated with this way of thinking about the combinatorics and the geometry, which we can later do loop integrals to get amplitudes. But the integrand itself is something which is handed to us in this picture. Certainly not something that's sort of obvious from the world line formula. Okay, so this is why it's not trivial to compare these things, and why it's not inconceivable that this is just a very different way of thinking about what string theory is, which really begins with something sort of fundamentally more unified and sort of strings without stringsy already at alpha prime goes to 0 with the surfacehedron, which then sort of miraculously blows up into this binary object that we can make sense of even at finite alpha prime. All right, so that's all I wanted to say. The final topic, but I think what we can decide how many people are willing to like stay up and talk about this, is where did this magic come from? So I explained to some extent where the surfacehedron comes from in general. So thinking about the surfacehedron, that's something that you can explain to a kid in grade 8. Okay, so it's all just adding vectors, even easier than the amplituhedron that you can explain to someone in grade 11. You don't even need to know anything about determinants. Okay, this is all about drawing curves on surfaces and relations, linear relations between them, and so on. Okay, so the surfacehedron is a very simple object. If you just want to, from there, go up to discover these binary geometries, then, and as was done in the development, it seems sort of rather miraculous that it's possible to give these guys a binary definition. And in the finite type cluster algebra cases, there is some explanation for it. But we're well beyond those finite type cluster algebra cases. And as I stressed, even the finite cases are not quite cluster. It's just dn hats and not dn, for example. So there has to be something deeper explaining the origin of these miracles. And that has to do with with Quiver categories. This really is one level of sort of abstraction beyond the things that we've been talking about in this subject so far. But I find it astonishingly beautiful. And it does give a totally conceptual, if quite sort of deep and alien origin of these binary geometry magic. But anyway, perhaps we can stop now and clap. And if anyone is interested in hearing anything about that, I'm happy to do that later. But this looks like a good time to stop. Thank you.
Great, thank you very much. I see some hands up. Good, David.
Yes,
you're
well,
applauding. David Broder, you have your hand up. Sorry.
Yes, thank you, Nima. Thank you to the organizers for scheduling this at the end of a busy day. I stayed listening, Nima, and I picked up several times during your talk, but particularly at the end, the following picture, that your stringification has nothing a priori to do with string theory. It's an ultraviolet regularization. And when you introduce your alpha primed, you end up with mathematical expressions at finite alpha primed, which are much more simple than those of string theory. And then you.
Well, we have integral expressions, but we have integral expressions. We're exploring what the actual functions look like and trying to compare them with what we get in. You see, the actual integral expressions in string theory look more complicated. But we're trying to compare what the final answers look like to see if physically they're actually the same. Right. It's certainly a very different representation. It's not clear as if it's actually the same in some hidden way or not.
So please go back to that very explicit expression for the one loop 4-point function that you gave.
Yes.
And make and when you show that, I'll try to ask my question.
Sure.
Hopefully without being interrupted.
Sorry about that. There.
Okay. So this is an amplitude, yes?
Yeah.
Okay, and it depends upon certain parameters and certain masses and regularizations. To what question is that the answer?
4-point amplitude in this trace phi cube theory.
And is this something that would be attained in the identical expression by different methods that you've done that economically via stringified expressions, which are
that's part of the problem. That is part of the problem is that, for example, in string theory, strictly speaking, for any non-supersymmetric example, there will be divergences everywhere because we have these tadpoles and mass numbers, all those things are divergent. So first of all, there's that. But we can ignore that and say, well, maybe we should compare. And so, but that tells you, first of all, that we're not going to on the nose match this function with something you're going to get from string theory. Because here we have something non-supersymmetric. There's no sensible non-supersymmetric string theory at one loop. Okay, so we're going to get all the divergences that we expect to get there. But you see, we would also have those divergences if I didn't sort of regulate this master normalization of the tadpole sort of by hand here. So you might think, okay, and those divergences in string theory are actually interpreted as generating a potential so the dilaton runs away and so on. So you might think that this is kind of this is a good thing. Maybe this is letting me bypass the sort of first obstacle, and maybe I should see what the S and T dependence looks like and compare that to what I would get in a sensible supersymmetric string theory. Or perhaps there is some version of this object that we're talking about here, which would supersymmetrize it in such a way that would remove all the dependence on these little m squared, capital T, and the capital M squared parameters. I don't know. Okay, but that's the 0th order difficulty for why we don't yet know how to just compare. Say this formula equals that formula.
So
what
I
we
want
can
to
do is look at the qualitative behavior, which is what I told you about. We can also look at the alpha prime expansion. That's something that we're looking at to see if we can sort of identify the kind of numbers that show up in the two expansions to see if there's any qualitative similarity there. But the answer to your question is no. Unfortunately, there is no sort of known string answer that would that I can directly compare to this, because there's no known string background that is not supersymmetric and allows me to do this calculation.
So it's an ultraviolet regularization of a question that doesn't exist.
It's the question exists perfectly sensibly in the trace phi cube theory, and there's a perfectly good answer. There, you see, in the trace phi cube theory, it's actually good to have all these parameters because the m squared is giving you the master normalization of the external leg. The capital T is the bev of the field phi. So it's all good. I mean, in other words, if you're summing these diagrams in the phi cube theory, then you would have, in addition to the usual ultraviolet divergences, which you'd have there in high enough dimensions, you'd also have these sort of stupid infrared divergences from the 1/0s in these propagators, right? And those we know how to deal with. That's just telling me I have to shift the vacuum. That's the tadpole. Or I have to shift what I mean by the mass of the particle. That's this guy here, right? So we know that, so in practice, we know that if I were to do these calculations in the field theory and I encountered these two diagrams, well, I know that here I just put in a 1/m squared instead of 1/0, and I put some sort of capital T there instead of a 1/0, and I would move on and I would do the loop integrals and I'd sum them. Okay, so I'm getting an ultraviolet regularization of that. Okay, so all the actual UV divergences, the non-trivial UV divergences in the loop integrals are all gone. And when I get this finite expression.
Thank you.
All right, any other questions? Wow.
It is nearly midnight Europe time anyway.
I think there might be some people in China too, so which I guess actually is not as crazy, but it was a little while ago. Well, if there aren't any further questions, let's all thank Nima again. Excellent job, Nima.
Thank you.
All right, we will reconvene tomorrow morning at in Europe. It'll be at 1 o'clock. Have a good night, everyone. Thank you.
Good night.